Welcome to the NYU Tandon School of Engineering. Thank you for joining us today for the latest presentation in our seminar series in modern artificial intelligence. Thank you as well to Tandon Executive Dean Juan de Pablo, who also serves as NYU's first Executive Vice President for Global Science and Technology, and Senior Vice Dean Ray Odell for their unwavering support. I'm also grateful to my own Department of Electrical and Computer Engineering for hosting us. 8 years ago, I launched this series with an ambitious goal to explore the influential research ideas of today that will shape our tomorrow. Watching it evolve into a significant event in the AI community and having the privilege of introducing so many renowned speakers to this stage has been among the greatest pleasures of my career. Today's speaker, Hongyang Li, is an assistant professor at the University of Hong Kong and has led the OpenDrive lab there since 2021. His research focuses on autonomous driving and embodied AI, and he created the first large-scale real robot ecosystem, Agibot World, which systematically investigated the scaling law principles for robotic manipulation. He was the leader of the end-to-end autonomous driving project UniAD, which has had a large impact both in academia and industry. He has served as area chair of numerous conferences such as CVPR, NeurIPS, iClear, ICCV, ICML, RSS, and his honors include the IEEE CVPR 2023 Best Paper Award and the China AI Wu Wanjun Early Career Award. Today, he will be discussing his innovative framework for learning cross-embodiment vision language action policies, enabling generalist robots to perform effectively across various environments. True to the mission of the series, this is influential research poised to make a major impact on the world. So without further ado, please join me in welcoming Hongyang Li.
All right. Thank you, Anna, and thank you all of the guys. I'm super happy to be here. This is a very short travel here, only 3 days. And I'm super fortunate to give the talk. So my talk today is going to focus on the visual language action, aka VLA models on the horizon for robotic systems. So the talk today consists of the following parts. So the first one is a little bit preliminary or introduction on the VLA, about the preliminary on the introduction and the roadmap. And the second part is a majority of this talk that consists of VLA for robotic system. Basically, I'll walk you guys through the UniVLA, our team's recent work published in RSS this year. And also, this is a large-scale robotic manipulation benchmark called the Agibot World, and is algorithm that named as Go1. So it is going to be presented at AROS next few weeks. And also, there is a recent work that we are working on to apply the VLA models to the humanoid. So basically, we want the whole body humanoid to perform the locomotion and also the manipulation simultaneously. And the last part of this talk concludes with the future challenges. With be cautious on the demo. I know there are lots of just fancy demos, and we should be very cautious on that. And towards the truly AGI in robotics, so what's going to be the future research directions in this field. So this talk will consist of 4 works. The first is we are going to see some recent advances in the VLA structure. How are we going to design the unified, the so-called VLA for many, many tasks, including the locomotion and navigation tasks. And for the benchmarking thing, so we are collaborating with Agibot. This is a very young startup in Shanghai. So we create this the many large-scale real robots benchmarks to facilitate. You're going to train the foundation model for robotics, right? So you need a lot of data. So that's why we create this data set. And beyond this data set, we also have this Go1 Pro or Go1 model for that. So G stands for Genie, so the hardware name. So the Genie operator consists basically the model utilizing the Agibot world. And also how to utilize this VLA into the humanoid. We'll have a little bit introduction. So this is just a recent submission to a conference. So the first thing, so what is a robotic manipulation, right? So this is a physical interaction. between a robot and the objects in its environment. So the task ranges from simple like pick and place operations to complicated dexterous manipulation, right? So this is a definition. So basically, we are learning a mapping from the observation to the actions, right? So the observation could be image depth or robotic appropriation, things like that. So for the output, this is an action from the, you can see the translation, the orientation, and the gripper. And for the learning paradigm, so we are all engineering background, right? So I wouldn't explain for that. We are utilizing, if you have the human expert, you will use the imitation learning. If you don't have, you will utilize the reinforcement learning to design some reward for optimizing the goal. And there is some recent industry news. This is a very popular startup company called Physical Intelligence. So basically, they want to divide the recipe to a generalist policy. So the biggest challenge between the biggest challenge nowadays, I mean, in the context of foundation models, is that we want to generalize a policy that could be utilized in multiple tasks or scenarios, right? So basically, the key recipe, there's no doubt for that, is just to scale up the diverse real-world data and utilize the imitation learning so that you can perform the long horizon dexterous manipulation or the cross-embodiment control from the Google team or the other, like, for example, recover from the failure modes, like how to fold any clothes. This is a really cool demo. I'll see a lot of startups doing that because this is a non-rigid objects, right? You cannot very easily to perform the simulation in the simulators, right? You have to rely on the real robots and the bimanual robot arm task is quite challenging for that. And also there is another company called the Figure that they recently have this Helix. This is a dual system to utilize a VLA. So we all know this is a foundation model and how to fast deploy into the real system, like for the onboard chip, is quite challenging. So this is why they have this VLA system, like system 2. This is for the foundation models to have deep thinking or deep planning reasoning for that. And for the system 1, they will have this efficient inference for the most tasks. So they would showcase the whole upper body control and also the multi-robot collaboration or the other, like, for example, human parsing task grounding things for that. This is a pretty cool demo. I think, I guess this is a coolest demo I've ever seen across the recent news. So this is a recent maps of a roadmap for the VLAs. So starting from the VLMs, this is could be seen as a base models like the Flamingo work or the Bleed from the Salesforce. And also we can see the GPT series of work. We have the Gemini, right? And we also have the Q1 from the Chinese giant technology startup. And also this is Stefan and ByteDance, the Bagel. So basically, the middle part, this is a roadmap from the foundation models. And for the upper part, this is this line of work try to focus on the embodied understanding of the environment. For example, you gotta have a understanding of the environment or how do you interact with your objects. So we have the PAMI-E from the DeepMind. We have also other amazing words. And for the this lineup of words, they focus on try to utilize the foundation model to control or to action or policies that you can actually execute all the policies. So we have the Robo Flamingo from this is from the ByteDance. We also have some collaborated with them, and also the OpenVLA. I bet you must know this very popular work to generalize the manipulation task to a wide spectrum of tasks, and also the Pi0 physical intelligence and Helix or other works. So VLA is so cool, right? So VLA is the only solution or not? So does it have any PVS or the bottlenecks compared to the conventional modular-based design? So our toy demos, this is demos from the UniVLA, our work. So we show that even the lightning variation or the visual distractors or the, if you change the manipulated objects from one to another to the novel objects, it will just basically doesn't work at all. So this is a little bit surprising for the foundation model, right? We expect that they can do a bunch of a variety of tasks, right? So we argue the challenges suffers mainly from three aspects. The first is it struggles to generalize, okay? So in terms of auto distribution, generalization, so we want to have the robot arm to grasp or to manipulate anything instead of just a simple setting. And it's not really dexterous, okay? So we want to have some system that could manipulate any non-rigid objects in like the human's hands do. And also it suffers from the edge side responsive control, meaning so the VLA cannot be deployed real time on the onboard chips. So I just list several endeavors from the previous work that try to resolve from different aspects. Is just to give you a hint that both the academia or the industry have already tried to resolve those aspects. So we might wonder, so what is or where is the so-called robot GPT, I mean the so-called AGI for the manipulation, right? So here we make an assumption to compare in terms of the data. So if you train the Llama 3, this is a quite famous work from the Meta team, and we want to compare on the same quantity. Let's assume like 200 words per minute and 1 token per word, okay? So if you transfer from the Llama, it consists like those kinds of hours, right? 700 million hours. So if you train GPT, it's like 400,000 hours, right? So if you train the Pi0 data, it's gonna cost you like 10,000 hours. So basically that's how are you gonna accumulate all this amount of data to achieve the generalization. So the OXE stands for the OpenXE embodiment, which is a collaboration work that I think this is a equal last year best paper finalist or not, I'm not sure. So this is a collaboration from like 20 research labs across the globe, led by the Sergey Levin's team. So you can see, you can get a sense. So the amount of data in robotics is much fewer than the foundation models or the foundation models in the computer vision or the natural language processing. So not even to mention how are we going to propose or create the foundation model in robotics, right? So basically data is always very scarce, or the scarcity of data is a true or the core issue. I mean, basically engineering effort is quite important or crucial to achieve the generalization performance, okay? So the current benchmarks in the robotics, either they have this short horizon task, and they have this simple task like pick and place. They have the control lab environment, okay? So this is a previous work from the from DeepMind, from the Stanford, right? So last year at this Cora, I think this year Cora is just happening right now, right? So it's Generalizable, this is a big guy from the computer vision. So we share similar background. We are all computer vision guy to approach the robotics rather than the robotics to utilize AI technologies. So basically there are three fundamental tasks across the robotics: locomotion, navigation, and manipulation. So this is his idea, right? This is not entirely my opinion, but I want to echo a little bit on the manipulation. So there's a long way to go. This is the focus of today's talk. So the big challenge, which I totally agree, is data. So this is much harder to obtain than the vision or language. So next, coming up, I'm gonna cover like recent work. How are we going to propose the new VLA paradigms or the architecture to improve the generalization problems? And how are we going to construct these algebra word data sets to fulfill or at least investigate the scaling law in this field? And due to time limit, I may talk a little bit on the variant of the Go1 model. Basically, we want to have this data distribution. So the conclusion is that compared to the data scale, we want to investigate the data distribution to improve the quality, to denoise some, to debias some noises, to ensure the quality. So the quality rather than the skill is more important to achieve the generalization problem in this field. And lastly, I'm going to talk about these VLA applications on the humanoid. So, the VLA, this is a UniVLA learning to act anywhere with task-centric latent actions, okay? So echo the previous data scarcity problem. So here, this is a data pyramid concept, which is quite popular in nowadays talking, including Yuke from the UT Austin and Guanya from the CMU, Xiaolong from the UCSD, and also Chelsea mentioned a few times. So at the bottom, we have the largest scale of actionless web videos. So basically, we can utilize the Ego 4D datasets. We can utilize a lot of datasets from the web data, right? And in the middle, this is OpenX datasets or action-embodied robot data. And on the bottom, on the top of this pyramid, we have the task or embodiment specific data, where it only takes like just a small amount of time, proportion, because of it's quite hard or expensive to collect the real robot data. So here, the motivation is that given the limited volume of transferability, we want to utilize this low-level action space, and we want to utilize how to, given this fact, so the data is very scarce in terms of the real data. So we want to extract the common representation, the so-called intermediate representation for the policy to execute on a variety of tasks or applications or different embodiments, okay? And so here we want to echo some previous approach. This is a very famous work, the latent action pre-training from the videos. This is called the LAPA work, where they utilize this encoder with the codebook for the latent action and decode the image or the state to reconstruct as a pre-training paradigm. So this is example from the denoised MDP. So the reference is here. So the goal is to let in as much sunlight as possible. So this is the goal we want to purchase. And we have the reward relevant stuff. So the sun is very important, right? But whether or not there is a plane in the air, it doesn't care at all, right? And there is a accountability problem. We have the reward, and we want to control the settings. So the sun, whether or not it's out there or not, cannot be controlled by ourselves. But opening the curtains is entirely controllable, right? So this area, this bottom left, this is the area we want to optimize or let the features be optimized towards this part, so to fulfill the goal. So the naive latent action, so this is a non-controllable or task irrelevant dynamics we want to remove entirely about that part. So for example, the appearance of new objects, right? So the human intervention or the movements on the non-ego agents, right? Those are considered as the task irrelevant features or objects or the data you collect for these for the pyramid, data pyramid. So we want to have this controllable and task-centric setting for that. So how are we going to achieve that? So this is a method of the UniAD in this work. So in the stage one, this is a language instruction. We want here, this is a language instruction, and you feed forward into this T5 backbone. This is a task-related dynamics, okay? And this is a task-irrelevant latent actions. So this is something that cannot be told from the language. So during the first stage, we have this pre-training stage. We have the encoder from the DINO V2. This is a semantically rich and object-centric. And this is a prediction target. So basically, we want to pre-train this part and obtain according to the language instruction. So those tokens are very useful, and we want to utilize during the fine-tuning stage. So during the stage two, this is we want to learn the task-centric latent actions. So the difference is that this is a pre-training stage. You want to utilize the web data or whatever data you have for obtaining a better backbone. So this is a backbone. But during the second stage, we will transfer or copy the weights here to do the fine-tuning on specific robotic applications. Okay, so we will replace with the yellow part with the language instruction to the red part on the task-centric latent actions. And this is a task-irrelevant part where we wrote as ATI. So the task-irrelevant latent actions, we want to decouple for that. This is a little bit detailed. I will skip for that. So after we have these like the tokens on the task irrelevant and relevant tokens, we will have like this heterogeneous action space to do the policies or the low-level policies to execute the policies. Okay, so this is an experiment on the Libre benchmark. We will have the different dimensions of evaluation. For example, the Libre spatial, this is the same object and unseen layout. So the task is pick up the ball in the top drawer and place it on the plate. And the robot arm will execute the policy in the simulation benchmark. And also have the Libre object, the goal, and the long horizon manipulation task. And we can see, so the UniVLA achieves, this is a new soda by pretraining only on the human videos because of the decoupling of the tokens. And we want to optimize the task-centric part by learning from the language prompt. And also here we want to echo, so UniVLA can also do the navigation problem. So basically you will remove the fine-tuning of the head part with the navigation head. So using a single frame RGB input compared to the Navid. Navid is a recent work from, I think from the Wang He's team. So this is UniVLA to achieve the comparable performance, only utilizing one single frame, whereas the Navid uses all the past history frames. So also this is a real world experiment. So basically there are 4 tasks, 20 to 80 demos for each. So the coverage will be the task deformable articulated objects and long horizon to use semantic understanding stuff. So we can see there is a big improvement from the UniVLA, from the previous diffusion policy or OpenVLA or the LAPA to the new this benchmark. And this is the same latent action across environments and across different embodiments, where we have different groups of picking up things, place things, or move forward, and things like that. And you can see also the zero-shot generalization capability on the unseen or embodiment gap improvement. And those are the more settings or demos for the Libre, for the different R2R different simulations. And this part is for the real world experiments, like putting a drawer into the cabinet. So we can see the UniVLA has achieved better results. And the next work, after investigating the VLA structure or how to design the internally the architecture, we'll look forward into the data part. Whereas this is a data set, this is a large-scale manipulation platform for the scalable and intelligent embodied systems. So this Algebra world, this is a large-scale, high-fidelity robot data sets. So the reason that I want to collaborate with this company is at the university, we never seen, this is actual factories, data collection factory in Shanghai, where they have that more than 100 robots in the flash. So we can accumulate the real robot data without considering any simulation, right? If you rely on the simulation, you're gonna face the 100 years question on the sim to real gap, right? You're gonna be asked a lot on the sim to real gap, things like that. So if we solely rely on the real robot, so here in this work, we want to investigate how much data do we need or acquire, or is there any scaling laws for accumulating so much data to improve the performance? So this is a fact sheet. We have the robot platform on the Agile G1. This is a gripper with visual tactile sensors. And also this is a 6-DoF Dexter hands. And we have for the data collection, this is a VR, the whole body motion capture control, so that you can accumulate the data from the human experts. So there are some features, including the long horizon manipulation and also the multi-robot collaboration, and also the moving object, like you don't really handle the static objects alone. And also this is a bimanual tool use. In some cases, you have to use your both arms to perform some task, right? Using only single arm will not suffice. So this is a visualizer. So basically, after the data set is released online, the robot, this is a Hugging Face organization research team. So the Rami from the Paris office, they just provide us a visualizer online. So we are very happy to see the community will contribute all together. So this is an all-purpose sensor setup with a lot of visualizations, including the multi-view RGB and the depth sensing, the visual tactile sensors. And also we provide a lot of metadata, including multi-level instruction, the camera parameters, the trajectories, and also the metadata to record or make a lot of meta tabs. For example, in this frame or in this time step, so the labeler will stop or by checking the data or the trajectory false. And yeah, it's basically just many metadata you can utilize to build on top and derive your own need of data sets. And for the data collection with human in the loop. So here we want to emphasize the data collection is of high standard, where we have on the edge, we have the data collection. And we have the validity verification, and also we will upload and processing to have the quality check on the cloud. I'll just skip that. So in order to create these data sets, so basically, Agile World, the company recruits like 50 labelers, human labelers, to do the annotation, to collect the data, like probably like at least 3 months to reconstruct the data to ensure quality. So for the data sets, the facts, we have these diverse scenarios and objects to include the real world, the controlled environment, to have the domestic, or basically we have 5 major sectors, including the domestic, retailer, and industry, and restaurant, and office scenarios to cover most cases in our daily life. So, so it covers diverse real-world scenarios. And this figure is interesting to mention, where we, to statistically draw a line here. This is a line of the number of trajectories across different, like, say the automatic skills. For example, all the verbs like pick, place, fold, push, is things like that. So if you compare to the other data sets, for example, the Droid, the OXE, OpenXE embodiment from the Google team, you will see it faces a long tail problem. So basically, this is probably one of the major reasons why if you utilize those data sets, it doesn't exhibit zero-shot capabilities to the unseen environment due to the data distribution problems. So if you have like a balanced distribution across different scenarios, or in terms of the core automic skills across multiple domains, it will the balanced data sets distribution will have guarantee a better generalization capability for sure. So given the data or benchmark is ready, the next level is to develop a model. So basically this goal 1, this is a model or the benchmark to have the algorithm to testify the benchmark. So the latent action model, LAM, learns a universal action representations from the web data. So for the model or the algorithm part, Agile World only consists of 1/4 of all the pre-training data the Go1 has. So we have the web scale vision language data, the cross-embodiment robot data, and also the human videos, okay? So this is a general pipeline, even from the OpenVLA. So the difference lies in the purple one. So we want to utilize, learn from the data pyramid, learn from the web data, from the synthetic data, from the real world data. And the difference is during training, pre-training, this is an image text, and we will have the vision language pre-trained. So with a feature extracted from, for example, InterVLA or the other backbones you have at hand. And also this is task instructions. So the purple one, this is a latent action. Okay, so for the OpenVLA or the previous work, they don't have this explicit part to extract the latent actions. So the latent actions is quite important. So basically, it will extract the useful, like the meaningful representation relatively relevant to these task instructions for the training. And then the blue part is just a regular practice. If you have the downstream applications, basically this is a DP or diffusion policy. It's just a few layers to fine tune the executed policies. So you can see this is a very informative figure. So Go1 outperformed previous SODA policy, for example, the RDD. So here, this is a different task, restore back, table busing, and this is the average performance for that. So from this pink part, this is RDT 1B model, and this is the so the cyan part. This is a Go1 without the latent planner. So from the 60% to the 60%. So this is a gain due to the large scale data set by pre-training on the edgeable world. And from the cyan part to the blue part, this is a gain from designing this latent planner. That's basically it's like 10% of gain in terms of success rate for that. And also we have more ablations on the edgeable world and also on the alpha data set. I'll skip the details. And also we'll have this number of training trajectories. So basically every sample point. So basically we have 3 sample points in terms of different skills. So this is a performance. We want to investigate a predictable power law scaling relationship, whether it will enter into the plateau or is it a exponential increase or is it just a linear. So basically in this paper, the investigation is linear because of the insufficient sample points. So in my opinion, the scaling law for the academia for the manipulation task is not that investigated to a great extent. We just see a very tiny proportion of the whole picture. So there's still much research space for that in this aspect. And also for the data quality. So here, if we want to utilize all the data trajectories, so definitely in the edgeable world data sets, there are going to be some abundant data for sure. And if we want to verify only like the high quality trajectories, we want to get the, for example, remove similar trajectories or remove similar objects. So for the verified data, so the performance even got higher for that. So the data quality matters. Here, this is this is the real robots verification. So this is a 4 times speed up for the table busing for the fold shorts and other pour water or web table. So you can see the algorithm is very robust to different varieties or changes to the environment. Okay, so definitely there are some failure cases. I know all the demos are very cherry-picked. Maybe in the future talk, I will provide some failure cases on the Go1 scenarios. So the reason, so this is the reason we want to have this extension on the Go1 Pro. So the diversity problem, okay? So we want to, we actually don't want to give people an impression that this is just a pile up of resources okay, so you get access to the large scale real robot data, you have the resources, you have the much GPU, right? So you could have those fancy experiments results, but instead we want to have an in-depth investigation on the diversity or the data quality behind these data sets. So this is a follow-up work. We have like the Go1 Pro, this is recently archived. We just submit to some article or yeah. So I will briefly talk about this work. So the algorithm or the motivation behind this work is this is a pipeline from the DP, the diffusion policy. I really find this very illustrative. So why diffusion works? So there are going to be some diversities in terms of expert diversity. You have individual operational preferences, and you have the stochastic variations. And for the this could be the complex multimodal distribution. Okay, and it's a sufficiently extraction model for that. But do we need all this expert diversity? So in terms of expert diversity, we have like, for example, the spatial diversity. This is a starting point from the blue part, and you have the task is to push this T-shaped object into the desirable green part. So you can place the initial, the gray part with various places, and you have gonna use the robot arms to push this target to the desired area. So you have the spatial multimodality problem, right? So those are the expected data you want to collect. But also you have the velocity multimodality, meaning so different labelers or different human labelers or even different embodiment, physical embodiment have different hardware settings. So those are the undesirable the so-called multimodality that you don't want to see or accumulate in the data set. So here, we design an algorithm, which I skipped in the slides. So we want to learn the desirable spatial multimodality and remove debias the noises due to different velocities. So we want to basically learn an average velocity to learn the reward model to get rid of that. So each sample will be curated to the mean velocity to get removed of these noise factors. And if you testify, so I just skip all the pipeline details here. So you can see only fine-tuned on a new task with only like 15 episodes. So this is a previous Go1 model. So it fails onto the task is to make a sandwich from the different ingredients. And so the Go1 Pro can manage the bread into the onto the plate. Okay, so the last part, we want to talk a little bit on the VLA problem to utilize on the whole body control task. So basically, this is towards the unified latent VLA for the whole body local manipulation. This is a really cool work that we just released. We haven't released, but I want to talk about more on that. So this is an autonomous humanoid system. We have the NVIDIA team. We have the Groot, an open foundation model for the generalist humanoid robots. And also this is a typo. This is a figure. The helix helix task. Okay. So this is a focus on the upper body task only. And also we have this is learning humanoid stand-up control across diverse postures. So I believe this is work from the Shanghai AI Lab, and this is a work from Beyond Mimic. So this deals with the pure locomotion task. And we want simultaneous manipulation plus the locomotion, aka the local manipulation. We want to have one single policy to execute different scenarios, or whether to do some tabletop operations and also do some moving or navigation problem at the same time. So how are we going to achieve for that? So the challenge, so one of the challenge is the scarcity of the local manipulation data. We have the table of manipulation, like I just mentioned, the Edgeball World benchmark. Those are all the large-scale data. We have the navigation on wheeled or quadruped platform, right? So those are all amazing works, but they all separate tasks, okay? Manipulation and navigation are all separate tasks. So here, maybe one way is to collect the human expert data via the motion capture. Okay, the task, the setting is to have the local motion and manipulation simultaneously at the same time. So the very first thing is to accumulate data, and through the motion capture. This is a recent demo that's shown just like maybe a few weeks ago from the BD, Boston Dynamics. This is a large behavior models helps Atlas find new footing. So basically, they will utilize this end-to-end manipulation. And how do they collect the data? So this is a human collector. So you will notice there is a bunch of camera mounted at the top of the ceiling. This is a very high expensive, to be honest. So we want to buy this equipment, but it's just cost too much. It's like to transfer to USD like 200,000 USD to equip like 16 cameras. Basically, these are OptiTrack high precision or high standard cameras to capture the poses so that you can transfer those poses to do the retargeting to the humanoid. Okay, so the camera, the robot camera, this is an input view, and also you can you can capture all the poses from the joints, and this is consists of the data part for your system to collect. But we argue the mocap data is potentially very expensive for that. So, and also there is another challenge. This is hard to generalize once the position is perturbed. So here, beyond the data scarcity to perform local manipulation tasks, this is an essential requirement on the position accuracy and the stability. So basically, we want to argue that for the manipulation task, those precise and stable locomotion control is very essential. Okay, so you can see it fails to place the box. So basically, precise and stable locomotion control is required, and very marginal errors or disturbance in the position accuracy. For example, if you just move this box a little bit, so it will occur the stability or lead to the task failure. So for example, this incorrect position and orientation to the manipulated objects. And this is an instability leads to slip out of hand. It's just a fall the box. So this is requires essential requirement of the position accuracy and stability. So how are we gonna use the VLA to achieve the humanoid local manipulation task? So this is a humanoid pipeline here. This is a general pipeline. I believe this work is among the very first field. I know, so many students or many teams try to claim we are the first something like this, right? Students always want to write something. So I just humbly named it. So this is a very few work that utilize the VLA to resolve the local manipulation task. So we have here on the image observation, we have the task instruction. So this is a high-level planner. So the high-level planner utilize the foundation models to have the VLMs, to have the action decoders to execute, to perceive the world, to do the planning, and eventually it will send out the upper body action and also the local motion command. So basically, this is the upper body action. So basically, you do something, manipulate something. And also, this is a local motion command marked in red. So you will tell to move, to stop, and to do something to the low-level controller. So the basically low-level controller, this is our RL policy. This is all the robotics focus on. So you see a bunch of works, recent work from the ECRA, from the CORA, they all working on this part. So local level under the specific command output by the high level planner. So basically, after this local motion command, you will have the RL training, you will do the behavior cloning, and you will eventually send out the lower command regarding the legs or the lower body actions. This is a unified latent learning. So basically, this is a general pipeline here. And I will talk about a little bit on the pre-training. How are we going to acquire the VLM part for that? So this is a unified latent learning. Remember the UniVLA? So we just utilize the idea or the philosophy here from the previous work. So in order to pre-train the VLM, so here we have this LAM framework. So the LAM recap, this is a latent action model with the unified latent. So by seeing the unified latent, we want to disassemble, we want to decouple the task-specific in locomotion and manipulation. And in the feature learning space, we want to unify them all together. So both the locomotion and manipulation provide supervision for the VLM, okay? So this is how are we going to train the backbone. And how do we collect or update data to train the LAM part? So this is a low-cost human data collection system. So this is my student. His name is also Haoran. So for the locomotion, this is a low-cost egocentric video. So the locomotion, we will intentionally collect the locomotion with manipulation task involved, okay? So the manipulation aware locomotion, that being said. And also for the manipulation, this is a large-scale tally-op manipulation datasets. Basically, we just utilize the Agile word datasets. So altogether, we will form this unified latent embedded learning for the LAM to learn. So to summary here, this is a data collection for the pre-training. This is a LAM. So we have this low cost. Basically, you just mount a camera here to have those data collected. And also, we rely on fewer data. For example, in this work, we only rely on the 300 hours of data compared to the 2,000 hours from the UniVLA due to the LAM structure. Okay, because we want to unify using this codebook, unifying all the manipulation and locomotion. So we have this LAPA. So basically, this is also the LAPA idea. So utilizing this unified latent, so you don't necessarily to have those whole bunch of data to put into the network to partially address the data scarcity problem that I just mentioned in the previous slides. Okay. And for another contribution, I could say, remember for the local manipulation aware locomotion, we want to have this precision and stability where we call the local manipulation oriented RL. So I know the wording seems a little bit complicated. So but basically, trust me, this is just works quite well. So for the precise locomotion, we want to have the controllable interface, and we have the position and oriented reward to guarantee the stable and consistent gait. And also we have this precise locomotion for that. So previously we have this work. For example, the command from the lower body would output the random velocity. But in this work, we want to discretize to basically tell the command, locomotion command from the high-level planner to start or stop or give specific instructions instead of random velocity. And also for the reward, right? For the reward, basically in the RL for training for the teacher. So we have this velocity tracking error transfer to the position or orientation aware kind of reward for that. So basically, we want to insert, for example, previously we have like random upper motion. So basically, a humanoid can execute different random actions, right? But if you perform the manipulation, you can constrain your action range or action scope to a specific range that could be considered as the prior to the system. So for stabilized manipulation task, we want to have this manipulation-induced disturbance to the system. Okay, so for this local manipulation-oriented, so aware, I could see that. This is a little bit weird wording for that. So we want to have this consciousness of the system to consider both the local motion and manipulation, okay? So basically this is LMO, RL. We have this RL policy here to have this precise local motion and the stable manipulation. And so this is a technical contribution apart from the pre-training in terms of data scarcity. So we have this high-level planner, we have this local motion command. So we have this do the optimization here to output the lower part for the humanoid to learn. And for the experiment, this is a very cute robot. This is a very small-sized robot. Namely, is X2 from the Agile world. So as for the real-world setups, we consider 3 tasks. The first is backpacking. This is grasp a paper bag and sidestep to a carton and then squat and finally place the bag inside. And for the box loading, squat to grasp a box, turn left, and place it onto a cart. And for the cart pushing, it includes grasp a cart handle and push it forward stably to the desk. So we can see this is a very important experiment. So each task consists of 2 subtasks, and in total there are 25 trials. So this is basically the number of successful trials it has. So we will see. This is approved from the NVIDIA team. This is OpenVLA from Stanford. This is our work. So with LMO, so the locomotion manipulation oriented, or the RL automation part. So if you compare these 3 works, we want to emphasize the effectiveness of VLA. Okay, so this VLA works, or the remember the LAM, right? The latent embedding contribution. So it can boost the performance from 40 to almost 80 for that. And if you compare the first row to ours work, so modular design, meaning this is a third-party off-the-shelf indicator. So basically, you first move or do the manipulation, do the locomotion, and then by some indicator, for example, another LM indicator to tell to stop or to perform the manipulation. So basically, locomotion and manipulation are separated. Compared to this whole body VLA, so this is a kind of end-to-end trained according to the pipeline that I just drawn. So you can see the global optimization or the VLA trained end-to-end will also increase the performance from the 60 to the 78. And we can see some visual disturbance. So because this is a data-driven robotic system for the humanoid, so we can see due to the data accumulation to train all together, for example, the backpacking, there is an unseen bag. So here, this is a seen during the training, but also we can inference with the data, right, during the inference. So this is an unseen bag, and also if you bought for this task of box loading, this is unseen objects that didn't see during the training, and also this is a cart pushing where the object haven't seen during the training. And this is a figure that this is a numerical results. I just skip that. So this is a last part of this work where we are going to show the demos. It's not quite clear or yes. Yeah, I will mute the sound here. So you can see it can have the local motion and manipulation simultaneously using a unified VLA structure and then put the box onto the card. All right. So the future challenges. So the last part, I know there are there are a lot of demos recently. So on the showing the fancy robotics demos or some VLA advances, right? We should be cautious for that. I recently read a blog in Chinese. The blog argues most current VLAs are upgraded behavior cloning. So it's only relying on the massive data or computing power to force performance, okay, to mimic the behavior or trials. So they suffer from the trajectory overfitting. So this is a demo, but in the real world, we were facing like the quite complicated scenarios of the objects, right? And this is a fragile to generalize and near zero success in the real complex task, okay? So is there any reliable path onwards towards the so-called, the AGI in robotics, okay? So I think there are major two missing pieces or at least the two aspects or directions to try to a lot of efforts. So the first is a scaling simulation, okay? So there is a gap, I know, between the real to render to the real. So I would strongly recommend you to read this paper on the real to render to real. Basically, they would scale the robot data without any dynamic simulation or the robot hardware. And also, there is another missing pieces on the RL part. So basically, by seeing the scalable, we mean without relying on any annotation, or we can accumulate the data with RL, because RL is very favorable in terms of it can capture the false failure data, right? And give some negative signal to the system to correct. So this is a really desirable property that we want for the robotic systems. And fortunately, we have seen some attempt. For example, robust autonomy emerges from the self-play. This is a work from the Philip and Latent team. This is a long-standing high-quality research group from the auto driving domain. And we can see there are definitely a lot of work to do for using the scalable RL to achieve the general goal of manipulation for sure. And last part, this is a takeaway. The large scale, high quality data is a key recipe for the manipulation, for example, the edgeable world. So also I give you a few examples on the Go1 Pro. This is a distribution debiasing to improve the generalization problem. And for the UniVLA, we have learned the task-centric latent representations to ensure the generalization and possibly save a lot of data. And for the whole body VLA, this is to learn the unified latents and manipulation-aware locomotion policy. So basically, enabling the potential end-to-end task paradigm for sure. And other challenges, including the sim-to-real and the scalable RL, is definitely going to be worthwhile to try in the future. So that all concludes my talk. I'm so happy to have a lot of talents from my group. And yeah, most of them are attending the call, I think, right now. So yeah, I'm happy to take any questions. Thank you. Yeah, sure. Go ahead.
For Go1 Pro doing the debiasing
Yes.
on the larger data set. For the Go1 Pro, you were talking about debiasing for the larger data set, but you didn't really have time to go into the details of how you selected which data would be used for the fine tuning. Could you elaborate on that, please?
Oh, yes. For the Go 1 Pro data work, we just utilizing the edgeable word. But instead, we want to distill or want to squeeze the data sets from the edgeable word to have, for example, originally it has 1 million trajectories. But for the Go 1 Pro, if you debias the noises and remove the velocity noises or the other part, and to let the model to learn the average velocity to have a reward model to do that, to execute the policy. So basically you can utilize 10%, for example, or the 50% of the original edgeable word data set for that. Yeah, go ahead.
Mm-hmm. For the after the experience you had with AG World, how important do you think would be to replicate that massive data gathering with other kinds of robots like quadrupeds or just normal manipulators?
So you mean the data accumulation or?
Yeah, the data accumulation you did, but like with real robots instead of like using simulators like many other people are doing.
Oh, yeah. This is a common question. So to be honest, our team, at least didn't do a lot of simulation. So basically you want to investigate the proportion in terms of the web data simulation and the real world data. So you wonder the percentage to utilize them, right? So basically we just equally distribute all the data for one setting, but there is no common practice as to how much percentage you are going to utilize in terms of simulation or web data or something like this. So one way, this is a really interesting problem. You just occurred me to another thing. So compared to the data pyramid, how about to learn adjustable like meta parameters in terms of the web data simulation or the real world. So you transfer from the data pyramid to some like adjustable data like spectrum, for example. You want to learn these parameters specific to different data sets or tasks. Yeah.
I think there's a question in the chat from UniVLA.
Yeah, okay. So the question is, since VLA seems to be the most popular approach in robotics, which direction do you think is better for research, sim to real, or training directly on real world data? So that echoes similar question that we have from the on-site audience. So I think so I do respect simulation, to be honest, but it requires a lot of data, a lot of efforts, or so like I said, you will gonna be confronted with the all the time with the question, with the sim to real gap, right? So in a nutshell, I think for the real rigid objects or for most pick and place objects, you can definitely rely on the simulators. We got a bunch of the simulators, SXSim or the CPN or the other simulators. But eventually, you'll be testified on the real robot. So if you have the resources or the environment, I would better suggest you to verify on the real world data for sure. I know there's a lot of issues that you're going to debug or play with real robots, and it takes more time for like to publish papers, but I would highly recommend, especially for the young researchers, to test around on the real world data for sure. And I believe there's a question here. Yeah.
I have a question for latent action model. So I remember you pre-trained the latent representations using a reconstruction loss on the image space. So is it correct to characterize the latent action model as a video generator conditioned on the text? Like, have you ever like reconstructed the video output of the action using the decoder in the
yes. Yes, that could be very promising directions. So basically, one way is to predict the next frame. And the method you mentioned is predict the next latent embeddings, or this is entirely another directions for that. So even the VJava series of the word models follow the pipeline that you mentioned, right? We actually did some experiments in our in-progress project. And it shows very promising results. I mean, instead of reconstructing the videos or images, just reconstructing on the latent embeddings, that could bring up at least two benefits. The one is you save a whole bunch of network or the data computer or something like this. And another for the robotics and the autonomous driving applications, actually you want to rely on the trajectories or the actions. So you want to directly optimize the action output. So this is where the latent embedding steps in. You don't want to reconstruct the so-called desirable or perfect image, right? So I think definitely this is a quite challenging, but still very promising or the correct directions. Yeah. Thank you. Oh,
Remember us?
oh yeah, sure. Oh, wonderful. Thank you.
And Harlan will just shoot us a quick photo.
Oh, sure.
You can bring your presentation. There.
Okay.
Great. We're gonna have a nice.
Yeah, that'd be great.
Yeah, like the. Perfect.
Sure.
Urs, do you want to stand to the photo? I will introduce. you
Yeah,
guys.
sure. Hi. Hi. Oh, yeah.
This is Urs Muller from NVIDIA.
Oh, yes. Yeah, sure.
Perfect.
Yeah, thank you.
Thanks so much.
Thank you. Yeah, nice to meet you.
So this is for
Worse.
Yes.
Okay, nice to meet you. Yeah.
Yeah, I'll be here for lunch and dinner. So.
Okay, yeah.
Thanks for a great talk.
Yeah, yeah.
I'm gonna pack it for you so
Okay,
that you
sure.
don't have to walk around.
3 days together. 3 days together.
Yeah, just 3 days. So I landed in Monday night, and I will fly back to Hong Kong this night.
Oh, okay. I misunderstood. I thought it took you 3 days to travel.
Oh no. Yeah,
Oh, okay.
it's such a short. Yeah, it is.
Okay.
Yes, that's right.
Sure.
Just want to know if the